And this is a project that Larry Hedges has been involved in now for 5 years. He's been on our advisory board.
That long?
And we're taking advantage of the
Has it
fact
been
that the
that
board
long?
is meeting tomorrow. And we've invited Larry to come and speak to us. So this lecture is sponsored by the School of Education and by the Institute of Behavioral Sciences. And you're here in one of our institute buildings. It's a great privilege for me to introduce Larry. It's a little awesome to look at his resume and his vita and go through his credentials. He has a very long academic title, so I'm going to have to read it to you. He is a Board of Trustees Professor of Statistics and Education, and that's a very distinguished honor. There are 1 out of 8. There are only 8 of these at Northwestern University, and Larry has 1 of those 8. He is also the Social Policy Professor of Psychology, and he is the Director of the Institute for Policy Research, QCET. So he is an internationally known expert in the area of statistics, educational statistics, and evaluation, which is what brought him here to us on our advisory board. So he has appointments in statistics and psychology and in education and social policy at Northwestern University. Before joining the faculty at Northwestern, he was the Stella M. Rowley Distinguished Professor, Service Professor at the University of Chicago. Larry's work crosses many fields, and that's because of his interest in statistics and evaluation. But he's best known, I think, for developing the statistical methods for meta-analysis. And he has published, I think, the classic work in that area, the Statistical Methods for Meta-Analysis, which was published in 1985, and more recently, the Handbook on Research Synthesis and Meta-Analysis in 2009. Larry is an elected member of the National Academy of Education. He's a fellow at the American Academy of Arts and Sciences, the American Statistical Association, the American Psychological Association, the American Educational Research Association, and he's a member of the National Education Science Board and president of the Society for Research on Educational Effectiveness. He was nominated by President Obama to be on the board of directors of the National Board for Educational Sciences, and he was confirmed as a member by the U.S. Senate in 2012. And finally, he was elected the Statistician of the Year by the Chicago chapter of the American Association the American Statistical Association for the year 2014. Despite all of that impressive academic credentialing, it's been interesting to watch Larry with his great expertise operating on our board, because with all of that expertise, I'm really impressed by the fact that Larry is a very gentle and kind reviewer. It's something that I notice that he is very careful with what he says. He's a very kind and generous person, I think, in his work and in the way he looks at evaluations, always with a very positive kind of outlook on how things might be improved, but very generous, I think, with respect to respecting the work that we review, looking at what kinds of programs and practices are effective at the evidence would support recommending it. So it's with a great privilege for me to introduce Larry. Larry, welcome.
Thank you. Del, that check is in the mail. You'll get it soon. That's just, in all honesty, it's really a pleasure to get such a warm introduction and, perhaps a little unfairly generous introduction from somebody that I respect as much as Del. And let me sort of start by saying this is a pleasure to be here. And my talk today may be a little bit controversial in some ways, but I actually believe that most of what I'm going to suggest has some logical basis, and I perhaps will discuss some of that. I'm going to talk about replication. And the reason I'm going to talk about replication is that it's really a central concept in both the logic and the methodology of science, and more importantly, in some ways, the rhetoric of science. There is a sort of philosophical set of arguments about replication being the underpinning of scientific knowledge. The whole Karl Popper explanation of why induction is a sensible way to draw inferences is based on a notion that science involves replication. Replication is part of the rhetoric of how science can be self-correcting. Errors are discovered through replication attempts, and that's why scientific knowledge, part of why scientific knowledge has a different status than other kinds of knowledge, because we have this mechanism for self-correction. In some areas of science, people will say that a finding isn't a finding until it's been replicated. And so replication fits into the status of even what is a finding in science. So given this sort of central place in the logic and in the methodology and in the rhetoric of science, you'd think that there'd be a huge literature on this central concept of science that we could draw on when we think about replication. But the fact is, surprisingly little has been written about replication and about the methodology of replication, and particularly what I'm going to focus on in this talk, the statistical aspects of replication methodology. One explanation for that may be that replication seems so obvious that special attention to method isn't necessary. Every scientist knows how to replicate findings, and so we don't need a lot of literature about this, a lot of thought about it. I'm going to talk about that in just a minute, but let me just say that in the plan for this talk, I'm going to focus on the last three things here. I'm going to focus on the proposition that the definition of replication, that is, when the results of study A are replicated by study B, seems obvious to many scientists. Or at least one possible reason why there isn't more research on the topic may be that it's something too obvious to do research on. Second proposition is that statistical analysis of replication may seem pretty obvious. It's fairly straightforward, perhaps. And lastly, perhaps the reason that there isn't very much work on the design of replication studies is that it is just as obvious as it seems. You want to know if study A can be replicated, just repeat it. Do the same thing all over again. Compare the answers. I'm going to argue that each of these three propositions is more complicated than it seems. And again, I'm going to focus largely on the methodological / statistical aspects of replication to try to make my case. Let me start with the proposition that surprisingly little has been written about replication. I hadn't really recognized that or thought too much about it until I read a paper that was in it was in a psychological journal. I'm not remembering exactly which one it was, that made essentially this point. This is a quote from Schmidt's paper. You'd expect a large body of literature on replication, providing clear-cut definitions on matters such as exactly what is a replication experiment, or what exactly is a successful replication. Furthermore, when you would expect to find guidelines on how to conduct replication, or maybe standard operating procedures on the issue. But he claims the opposite is true, and as I began to think about it, I recognized that he was right. There is very little written about these details of replication. It's not true that there's no literature on replication, but a lot of it is a very high level of abstraction. It's more on the level, it's actually quite a bit in philosophy, but with respect to the social sciences that I know most about, most of the literature is about things like defining kinds of replication. And I'm not going to spend a lot of time on this, but I'll just point out, just want you to know that I know about this stuff. Because many of you know about it, and I don't want you to think that I'm completely ignorant of it. Fisher talked a lot about robust replication as a scientific strategy. That was very important in his conception of how we learn from doing experiments. But Seymour Sidman has wrote about replication and talked about the kinds of replication. There was a paper by Lycan in Psych Bulletin in 1968, and then a more recent paper just to give a flavor of the literature. This isn't all the literature. These are some of the kinds of papers that you may have seen as social scientists. And there's a crucial distinction that's often made in this literature between something you might call direct replication and something you might call conceptual replication. Those are the terms that Schmidt used in this 2009 paper, but they have analogs in some of these other treatments of conceptions of replication. And I'll start by saying I'm going to focus today primarily on the idea of direct replication, and that's repetition of an experimental procedure to see if you get the same answer. My take on the lack of literature in the area is probably that most scientists really do seem to think that the design and analysis of replication studies is pretty straightforward. They think they understand what they mean by that, and they think that designing and analyzing such studies is fairly straightforward. And really what the rest of this talk is about is I think it's not as straightforward as most scientists think. There's a replication crisis in some areas of science. Some of you may have seen this paper back in 2005. My friend John Ioannidis wrote it. It has a snappy title, Why Most Published Research Findings Are False. It appeared in a highly prestigious outlet, PLOS Medicine. John is a medical researcher. He runs a research center at Stanford right now, although when he wrote this paper, he was a struggling epidemiologist in a small university in Greece, but his work in this area has been good for him because now he runs a research center at Stanford in the med school. So John got some attention with this paper, perhaps due to the snappy title. He wrote another paper the same year that got attention. It didn't have such a snappy title. It was called Contradicted and Initially Stronger Effects in Highly Cited Clinical Research. And in this paper was actually, in some ways, more deeply substantive than the first one. What John did was to look a few years before 2005 and identified a set of highly cited clinical research papers in medicine. Highly cited was defined as being cited 1,000 or more times within 10 years. In my book, 1,000 citations is pretty highly cited. And then John asked the obvious question, have any of these things been replicated? And if they have, did they get the same answer? And if they have, and if they didn't get the same answer, did they get stronger or weaker effects? And the findings surprised the heck out of a lot of people in medicine because they found, A, that these highly cited, very important research findings did not replicate all that well. Many of the studies didn't replicate. The ones that didn't replicate, usually, almost without exception, there were smaller effects found in the replication studies than in the original study. And even the randomized clinical trials didn't fare as well as people thought. The quasi-experiments fared worse. It's fair to say. The quasi-experiments replicated much more poorly than the randomized experiments. But even the randomized trials didn't fare as well as people expected. This was a surprise. And it was taken seriously. And it was taken seriously in a couple of ways. It spawned a whole industry within the medical research community of what's now called meta-research. That's John's term. And we found that it wasn't just highly cited clinical research that didn't replicate. It was lots of other things that didn't replicate. So, for example, I'm just going to show you some props now, some examples of papers that appear in very good places that identified empirical findings, empirical examples of non-replication in the medical sciences. So people looked at the drug discovery literature and looked at in-house projects and used and basically tried to replicate published findings in their own development laboratories. And this paper in Nature Drug Discovery suggested that lots of stuff wasn't replicating. In fact, it was only a tiny fraction of the stuff that they tried to replicate that appears to have replicated. It isn't just sort of drug discovery projects that don't replicate. Animal studies don't replicate so well either. This is another paper that appeared in Nature. I mean, both of the, just to remind you, Nature and Science are two of the most important journals in science, so this is not the lunatic fringe here. This is the absolute center of high prestige science. Turns out animal studies don't replicate nearly as well as people would have thought that they would. And this is an example of an attempt in the ALS Therapies Development Institute to replicate certain animal studies that had been published. So the moral of the story is there appears to be a replication problem in many areas of clinical medicine. That led Nature to do a survey of scientists and ask the question, do you think there's a serious reproducibility crisis? And this graphic shows the results of that survey of scientists. 52% say yes, there's a significant crisis. 38% say there's a slight crisis. Now, I don't know how you have a slight crisis. This is a little, the terminology is a little odd to me. But if you sum those two together, you see that 90% of the scientists who responded to the survey said there could be reproducibility problems in our sciences. Now, you might be saying, well, these guys are just the lunatic fringe of science. They're probably in some obscure areas where nobody thinks the science is any good anyway. It's all the parapsychology researchers who are responding here. But you dig into the survey and you see that in answer to questions like, have you failed to reproduce an experiment? Either one of your own results or somebody else's, that chemists and physicists and engineers and people doing earth science and people in the sort of generic biological sciences are responding in ways that suggest that this notion of a crisis of replicability isn't just an isolated phenomenon that's happening, in the very fringes of science where you might expect there to be reproducibility problems. This is happening in the core of the hardest sciences that we know about, and it's to be taken seriously. And by the way, you're going to find that I'm going to make references to harder sciences than our own throughout this talk, in part because I think we can learn some things from them. Mimi, yeah?
Sorry to interrupt there.
Yeah. No, you don't need to be sorry. You can interrupt. The rest of you can interrupt too. But I will just ask that if it becomes a question of argumentation, if it's a question of clarification, do interrupt. If it's a question of argumentation, if it gets too long-winded, I might say let's do the argument at the end. But even a little argumentation is okay.
I'll keep it speedy and it's not argument. But a part of something that's missing here for me and what Nature did is like a piece of this crisis is that if you had asked these folks, did you publish the failure or attempt to publish? Like that's where an interesting.
Absolutely, absolutely. By the way, I wouldn't. As a social scientist, I wouldn't, I would ask a lot of questions about this survey. I say, so you had an online survey and a whole bunch of people responded. Well, how are the non-respondents different from the respondents? Maybe you're getting the nutcases to respond to this. And I take that. This is less to say you should believe any of this in very fine-grained detail, more to say, there's at least a lot of people out there that are worried about some of this stuff. And questions like, Yeah, and questions like, oh, did you try to publish that non-replication? You know, what happened? You know, did you publish that, and you know, did that result in in people saying, oh my gosh, we got it wrong, and now it's fixed? We don't know about that. However, this idea that there are replication problems in medical science has gotten into the popular literature. Here are some examples from The Economist. There was an article in Newsweek about this, and John Ioannidis was cited in both of these, in both the Economist articles and in the Newsweek article, as being one of the ringleaders in uncovering this failure to replicate in the medical sciences. And this, I think, caught the attention. Once it started getting into the popular, well, even before then, but certainly once it started becoming something that was discussed in the popular culture, the powers that be in medicine realized they were facing an existential crisis. And part of my pitch to you today is that science is treated specially by society for a particularly good reason, and that is that we're supposed to be producing knowledge that has a special status. It's different than other kinds of knowledge in the sense that it's supposed to be self-correcting, it's supposed to be replicable. You know, all the virtues that we tout in the rhetoric of science are the reasons why we can expect society to support us by giving us cushy professorships and big research grants and beautiful buildings like this in which to do our work. That's a cost to all of society, and and the reason we get this stuff is because we're supposed to be, part of that contract is we're supposed to be producing special kind of knowledge. And a replicability crisis, as they began to face it in medicine, undermines those claims of the special status of scientific knowledge, and it undermines our special claims on societal resources. And so I think we have to pay attention to this, is sort of my plea. Well, medicine did, and in various ways. And you see, this is, again, just a prop. It's an example of an article that was appeared in Nature, maybe not surprisingly, by the director of the National Institutes of Health, explaining how NIH was fixing the problem. And you know, there's a and it isn't just NIH, there's a widespread sort of set of efforts in medicine to fix the problem. And I think the reason why the high-profile medical folks are going public about their attempts to fix the problem is because they sense an existential crisis if they don't get ahead of this, or they don't let it get too far ahead of them. Okay. What does this all have to do with any of us? I mean, we don't do medical research. I think probably nobody in the room does, strictly speaking, you know, biomedical research. Some of us do work that's really on the fringes of that. So we could be influenced, but that's not by it. But that's not really the reason I'm talking about this. The replicability crisis has reared its ugly head in psychology, and that's pretty close to home. Some of you may know about, I'm probably sure all of you know about the Center for Open Science. Some of you may have seen this article, and again, this is just a prop. It's an example of a study that was organized by the folks at the Center for Open Science, in which they took 100 important psychological research findings and got 100 labs to try to replicate each one of them. So in other words, there were 100 findings, 100 labs, each lab picked an experiment to try to replicate. And the result was a paper in Science, and I'll point out that that's significant because this is the most important journal in science, arguably, and the results were not encouraging. Now, I don't want to go into great detail about all the methodology or whatever. This is just a sort of high-level sort of view of it. This got a lot of attention. You know, APA put out a big statement. APS put out a statement about it. You may or may not have seen this article in Science, which is more or less the same thing as the previous one, except done with experimental economics, experiments in economics by a set of economists. They picked a set of 15 or so findings in experimental economics and got labs to try to replicate them. And again, their spin, the empirical results aren't that much different. The economists have a better spin on it. They say, well, it wasn't as bad as it might have been. Although in some ways you probably would be hard put to say that this is a whole lot better results than the psychologists found. Okay, that's sort of the intro. So now I want to talk about the three problems I mentioned that I would talk the most about in this discussion. And the first one is defining replication. In order to I think that in order to get very serious about formalizing subjective ideas about replication in a way that would make a statistician like me happy, we have to talk about a little statistics. And those of you who know much about meta-analysis will sort of see immediately that my focus looks a lot like the kind of focus you'd expect somebody who worked in meta-analysis to have. Because meta-analysis deals with summarizing research findings across studies, it's sort of, I would argue, immediately relevant to the question of thinking about replication. So the fundamental principle that I'll start with is that a study's findings are summarized by some kind of effect size. It could be a mean difference, it could be a regression coefficient, it could be a log odds ratio, it could be a standardized mean difference or correlation, or any of the standard indexes of effect size, or any of the other standard indexes of treatment effect that we use in intervention studies. And I'm not going to do a lot of heavy-duty statistics here, but I am going to introduce a few symbols because the concept's important. I'm going to say let's use the symbol theta, the Greek letter theta, to represent the study's true result, the effect size parameter. And the idea is that theta is the effect size we'd observe if it weren't for the perturbating effect of sampling. So if we had a sort of an infinite sample size, if there was no estimation error due to sampling, theta is the result of the study that we'd observe. But of course, we don't have an infinite sample size in studies. We observe an estimate of theta, but not theta, and I'm going to call the estimate t. And I'm going to say, for the sake of argument in this talk, let's assume that the variance of the estimate t is known, and I'm going to call that v. This is a pretty decent assumption for most effect size estimators we use in meta-analysis. And it's close enough to being true for the others that everything I'm going to say in this talk would not be particularly affected by whether the variance was exactly known or was, had a slight amount of estimation error in it. So the setup is that we stipulate that a study's true result is some effect theta. We don't observe theta because of the uncertainties introduced by sampling, but we do estimate theta with some estimate t. And so this could, you could have the population standardized mean difference as theta, and the sample standardized mean difference is t. There's nothing particularly profound about this. Okay. The next point is, I think, not too controversial, because theta is conceptualized as the true result of the study. Theta is what we test hypotheses about when we do statistics. We test the hypothesis. If theta is the treatment effect, we test the hypothesis that the underlying treatment effect parameter is 0. Or if we're not testing, we're estimating, we estimate theta. So my argument is that if theta is the result of the study in a conceptual sense, then any definition of whether one study replicates another has got to be defined through the thetas, not through something else. And so if we let theta 1 and theta 2 be the effect size parameters of a first and a second study, and if we let T1 and T2 be the effect size estimates of the first and the second study, then we're in business to actually think about defining what we mean by replication. Given that the thetas are the true results of the studies, then one definition of what we could mean by replication is what I would call exact replication. If the underlying true effect in study 1 is exactly the same as the underlying true effect in study 2, studies replicate. And if they're different, then the studies don't replicate. And this is a definition of replication. It's be more precise, it's the definition of effect homogeneity that's used in meta-analysis, but I think it's a very sensible way of at least it's a sensible, possible way of talking about replication in any field. So everybody's with me on what I'm saying could be a definition of replication. Okay. Well, if you're with me, now I'm going to tell you that exact replication is logically appealing, but it's too strict for scientific purposes. And I don't mean our science, I mean any science. Real studies in good sciences don't replicate exactly. That's an empirical fact you all ought to know. And part of the reason I want to shift back and forth between the physical sciences and the social sciences is because most of us are willing to stipulate ahead of time that the physicists know what they're doing, that they have a science that has produced a lot of benefits for society, seems to be able to explain the world pretty well. You know, nobody feels inclined to lecture physicists about, you know, how unscientific they are, and they should really, you know, need to learn a lot more about science if they want to, you know, be in the big leagues. So what I want to do now is just sort of try to substantiate this seemingly crazy statement I just made. And I'll give you 3 examples, the last 2 of which I'll go into more detail on. There was a great paper in the Annals of Statistics in 1977 in which Steve Stigler, who is a noted historian of statistics at the University of Chicago, asked the question, do we need robust estimators? I mean, he was asking an arcane sort of statistical question, and he was looking at different sets of physical data and asking the question, do we need fancy estimators that take account of outliers, you know, that are resistant to the effects of outliers and stuff like that? And the important thing for this talk about that paper was that his conclusion was, no, you don't need these fancy outlier-resistant estimators to get the right answer. Of course, what Steve was doing is he was looking at historical physical data. Then we have modern physical data that's much more accurate than the old historical data. So he knew what the right answer was, pretty much, from the modern data. And he could look at the old data and say, well, you know, if I'd been around in the 19th century, what would have been the right thing to do? And he's sort of using this as a paradigm case. And his conclusion was an interesting one. He said, well, you know, 10% trimming is all you really need to do. Now, what he meant by 10% trimming is throwing out the 10% highest values and the 10% lowest values in the collection of data. And if you then, you know, average what was left, you did pretty well. Throwing out 20% of the data might seem like a little bit of a heresy to most of us, and more on that later. The particle data group is a group headquartered at Berkeley, UC Berkeley and CERN that has been doing meta-analyses of data on particle physics for the last 50 years or so. Every couple of years they publish something called the Review of Particle Properties, which is about this thick. It's now online, so, but when it used to be in paper form, it was about this thick. Hundreds of meta-analyses of all the high-energy physics experiments done worldwide to try and establish accurate values for the parameters particle physics experiments we're trying to estimate. Good science being done in large accelerators with, I mean, in some ways, you know, it's the king or queen of big science, you know, huge particle accelerators, hard to get time on the particle accelerators, individual experiments cost millions of dollars. And the particle data group had a lot of experience in combining evidence across those studies to try to estimate particle properties. I'll tell you an interesting thing about the particle data group's procedure, which is that they throw out about 30% of the experiments on the average when they try to average values to estimate things. Not always just because they disagree with one another, but sometimes because that's one of the reasons they throw out experiments. And then the third example is kind of near and dear to my heart because the first work in meta-analysis in physics was done in this area. There's a set of fundamental constants of mathematical physics that are really the centerpieces of a lot of the understanding of the physical world. And as early as 1929, people were recognizing that meta-analysis of a sort was, I mean, they didn't use that term, that hadn't been invented yet, and so they just called it reviewing. But what they were doing was quantitative combination of estimates from different experiments to get better estimates of the fundamental constants of physics. Okay? So let's see how well experiments agree that are estimating the fundamental constants of mathematical physics. Here is a picture of historical estimates of the speed of light and a confidence interval around those estimates. Now, the little dot in the middle is the point estimate, and the whisker represents the width of the confidence interval around that estimate. And this illustration is taken from a 1986 paper in the American Journal of Physics. So you see the 1984 value is the dotted line there. And I'll just remind you what this picture should look like. Since we know physics experiments always agree, all of those dots should line up more or less on the same horizontal line, and you'd expect it to be real close to the 1984 value. But that's not what the data looks like. You see there looks like that there's a time trend. And here in the early part of the 20th century, kind of looks like the speed of light is getting smaller. And in fact, there were physicists up until about 1940 who actually advocated that maybe the speed of light isn't constant after all. Maybe it is changing. There's a secular drift. But then new results seem to show that that probably wasn't really right, that speed of light really was constant, which is what the majority of physicists believed. And what you probably think you see a little bit later in that picture is that all the estimates are stabilizing perfectly. But if you begin to look at, if you expand the scale of the more recent estimates, you see that, in fact, well, they're stabilizing, but there's still a lot of variation. Well, maybe the speed of light's a difficult constant to estimate, and it's the outlier, and other physical constants behave differently. You know, in other words, maybe I just set you up by picking the worst example known in physics. Well, if you look at 5 other fundamental physical constants with the same kind of picture, here's a picture of the historical trend in estimates of the fine structure constant, actually the inverse of the fine structure constant, which is something that's important in quantum electrodynamics. It doesn't matter, you know, what it is. Planck's constant, the charge of the electron, the mass of the electron, Avogadro's number, you know, number of molecules in a mole. The agreement ain't that great. And for any one of these, you could, I will just assert without showing you the computation, there's a statistically significant difference among all these estimates. So exact replication fails for all of these constants as a way of describing the physical world. Now, the physicists aren't too worried about that because they understand experiments have biases and that a good experimenter tries to reduce biases, but you can never eliminate biases. And so part of how they deal with this stuff is to say we got to do better, but the degree of variation among results tells us something about how big the biases we aren't controlling are, and that should enter into our computation of what the real uncertainty of the findings are. Let me give you 4 other examples, just so you'll, again, just to illustrate the point. You know, here is the results on the fine structure constant presented in a somewhat different way. There is a historical comparison of estimates of the mass of the proton. That comes from the particle data group, by the way. And you'll see that the mass of the proton changed by 5 standard errors over a decade, which I'm sure isn't true physically, but if you believe these experiments and expected that they had resolved all of their biases or somehow taken account of all of their uncertainties, that's what this picture means. You might think that, you know, some of the examples I'm giving you are from earlier papers. Well, maybe it's all been wrapped up, you know, in the last few years. Here is this is from the most recent redetermination of the fundamental constants of mathematical physics, done by the CODATA, an international group that does this kind of stuff. And you know, here's what the experiments tell us about the universal gravitation constant. The operative word is constant, And if you looked across all of these experiments, you would not be able to tell. There's 5 times as much variation across experiments as you'd expect given the uncertainty of each experiment. What this led CoData to do in establishing the 2014 value was to multiply the uncertainty of each experiment by a factor of 6, because that would then bring the variation among the findings, that would make the variation between findings consistent. If everybody had underestimated by a factor of 6 the actual uncertainty of the experimental results. And one more example from the 2014 determination of the constants. This is Planck's constant. Again, the operational word is constant, but these experiments don't agree very well either. So I think exact replication is probably not a scientifically useful way of thinking about what we should expect experiments to do in a science that's pretty well developed and in which the experiments agree pretty well by the standards of a science. And essentially, this is not rocket science. I'm just saying, well, look, if the problem is studies don't agree exactly, even in good sciences, then what we have to do is develop an understanding of the fact that there small differences among experiments ought to be expected. And one way to define it, if you only have 2 studies, is by some kind of tolerance for the difference between effect parameters. There is some reason, which I could give you the argument for, but it's probably not so important to do it now. I'll just ask you to bear with me. There's some reason to think about quantifying variation of study results in terms of the squared difference and standardizing it by the variance of the difference. This quantity lambda is a quantity that there's a bunch of reasons why it's a reasonable quantity, which just bear with me for a while. We could argue about that later. You can generalize this nicely to a quantity that works if you have more than 2 experiments you want to compare. But one strategy, and it's not a completely fanciful strategy, for coming up with a scientifically useful definition of replication is to define some value of this quantity lambda as being negligible. Of course, if you have exact replication, then lambda is exactly 0. But the name of the game in trying to define approximate replication is coming up with a definition of lambda naught, some amount of replication that is, some amount of variation across replications that's taken to be negligible for scientific purposes. It's not 0, but it's not big enough to be important. Now, you might say, how could you do this? Sounds impossible. Well, the particle data group has been reviewing studies for 50 years, and they've got a definition. They think that lambda less than 1/4 is negligible, and if you don't believe me, you can look up the latest review of particle properties and see where they say that. In personnel psychology, there's this idea of the 75% rule, which was promulgated by Hunter and Schmidt, not the same Schmidt as I cited earlier, but a guy who works in personnel psychology. And the basic idea was that if, of the 75% rule, is that if 3/4 of the variation among study results is due to sampling error, estimation error, then the remaining 1/4 is probably negligible. It's probably explainable by other biases. But this has gotten pretty wide acceptance in experimental personnel psychology, and so that turns out that criterion can be reinterpreted as lambda is less than 1/3. In medicine, the Cochrane collaboration, which does big meta-analyses, systematic reviews in medicine, actually has a handbook of how to do this stuff. And in their handbook, and I can even tell you the page number, they say something that implies that lambda less than 2/3 is not important heterogeneity among studies. In other words, negligible. Now, the point I want to make about these conventions is, A, that scientific communities were able to develop them in the first place, which you might have doubted, Secondly, that they're all of the form lambda is smaller than lambda naught, where lambda is this quantity I defined a little earlier, the standardized squared difference among effects if there are only two. And I'll just say the last line is that actually in all of these contexts I talked about, the first three statements of the rule are the statement of the rule when there are only two studies. There are more than two studies, then the statement of the rule actually involves the number of studies, and so the actual thing that has achieved a social consensus is the last line. But if you put k equals 2 in each of those formulas, you wind up with the consensus that I suggested. Yeah.
Am I correct to interpret like the 2/3 there as
Yeah.
if it's an effect size, like an effect size metric? So that would say that the 2/3 there, as long as the average difference in effect sizes was under 2/3 of standard deviation. And is that the correct interpretation?
I have to think about it. Lambda is the squared. It's not quite because there's a square in there, so you have to take the square root of 2/3, and so then you're standardizing not by the individual effect, but by the sum of the variances of or the square root of the sum of the variances of the individual effect. The point is you can work that out. I mean, without saying I did the algebra in my head and I got it right now, which I'm reluctant to do because I've usually gotten it wrong when I try to do this in front of a bunch of people. But the point is there is a little calculation like that you can do that will give you an exact characterization of what this means in terms of effect sizes. And if you have more than two studies, there's a way of expressing things like what the average difference among effect sizes would be in terms of lambda. It's a way of understanding. So
we could come back to it later.
Yeah.
This is an interesting point that it just seems that direction matters a lot, right? Because you could characterize that in terms of, you could find a way to characterize it in
Yeah.
terms of effect size, but it matters a lot whether, even if you're 0.2, if that changes it from a negative finding conclusion
to a positive. We're going to get there in a minute. And actually, I think you're right. But the thing I would say that past experience seems to suggest, based on the medical stuff and other stuff, is that replication effects don't get bigger. They get smaller. And so I agree with you, direction's important. What I would say, sign is important. The difference between one study and the other, I think, is not important. But whether they have the same sign is real important. Because it changes the interpretation. Okay. So suppose you buy this idea that in hard sciences exact replication is just too tough a criterion for them to meet, and we shouldn't expect our own sciences to meet that criterion either. Otherwise, we're just shooting ourselves in the foot, saying, "Oh, well, we can do way better than physics." And I'm not on that train, even if it's leaving the station. So what should we do? Well, I'm suggesting we should try to come up with some reasonable criteria for negligibility, and then we should carry out our work with that in mind. So major point one here is that defining replication is not as simple as it seems. Exact replication is logically appealing, but approximate replication is more scientifically useful, but it's not nearly as simple, because it involves establishing social conventions among scientists about negligible differences, or what I'm calling lambda naughts. And there's no reason to think they should be the same in every field of science. Experimental psychology and social psychology might well come up with very different conventions for good reasons. Prevention science might have yet another. But I want to now turn to statistical analysis of replication, because I don't think that's as simple as people think it would be either. I've already said that that if you wanted to test exact replication, there's a way to do it. There's this statistic which I'm calling Q up here, which is the two-study special case of the more general heterogeneity test that's used widely in meta-analysis, by the way, by physicists as well as by psychologists. And when you have exact replication, Q has a chi-square distribution, so that's what makes the test possible. You could ask, well, I picked this statistic out of the air, why should we pay attention to this one? There could be other ways to do this. And my answer is, well, the Q test happens to be the likelihood ratio test, which means that it has some optimal properties. It's the uniformly most powerful unbiased test, so it has no other test, discovered or not, could be more powerful than this one. Might be just as good, but it ain't going to be better. And we have deductive theory that proves that. It's one of the great splendors of mathematical statistics in the 20th century. Okay, so well, how do you do a test of exact replication? Well, you just compute the Q and you compare it with the critical value of a chi-square distribution with 1 degree of freedom. If you're doing an O5 test, that's 3.84. So doing a test for exact replication is easy. But I just want to remind you of something before we get too worked up about hypothesis testing and how simple it is. Rejection of the null hypothesis is usually thought of as conclusive, but failure to reject isn't. So any test for exact replication kind of puts the burden of proof on non-replication. You know, in the following sense, that you only conclude you have non-replication if the test comes out significant. So unless the test has high statistical power, you may be fooling yourself. You may be saying, oh, I tested for non-replication. I didn't find it, so we must be replicating just fine. Well, I tell you now the power of that test was 7%. Then you're kind of in the position of saying, oh, well, if there really was non-replication, then 93% of the time my analysis wouldn't have found it. That's not very strong evidence. I would call that extremely ambiguous evidence about replication. So if we're going to be playing the let's test for replication game, especially if we put the burden of proof on non-replication, we have to be very aware of sensitivity of tests and statistical power. Tests for approximate, now this leads to tests for approximate replication. It turns out you can use exactly the same framework as for testing for exact replication to test for approximate replication. The only thing that changes is the critical value. And now the critical value for approximate replication is going to depend on the lambda naught. What do you mean by negligible difference? And so the real punchline of this slide, and the only point I'm going to make about approximate replication is that, check this out. You compute the very same statistic to test approximate replication as you do to test exact replication. The only thing that changes is the critical value. But wait a minute, the 5% critical value for exact replication is 3.84. If your definition of lambda naught is a quarter, then that critical value goes up to 4.76. And if your definition of approximate replication is the one that personnel psychologists use, the critical value goes up to 5. And if your definition is the one the medical researchers use, your critical value goes up to 6. So it's harder to reject approximate replication than exact replication. If you think about that, the logic of that going to make sense. But what that means is tests for approximate replication are less powerful than tests for exact replication, and that's really the punchline here. So approximate replication may be the scientifically right thing to do, but the tests are going to be less powerful, but we still need to have high-power tests to have unambiguous findings. And I'll just make one other point that I won't really expand on, and that is that you could turn this whole hypothesis testing thing on its head and say, wait a minute, I want to reject the null hypothesis to say my research hypothesis is true, and if I'm investigating replication, I want to be able to conclude that replication is the state of the world. Well, then what I should really be doing is setting up my hypothesis testing framework so that non-replication is the null hypothesis and replication is the thing I reject non-replication for. And there's a way to set that up, and you can do it with the Q statistic, and it's sort of boils down to rejecting when you get small values of Q rather than when you get big values of Q. And the details, again, aren't important, but just the thing that is important is there are at least 3 different analyses you could do that are perfectly logically, statistically justifiable to test for replication, even assuming you buy all the rigmarole I gave you in the first point. But they place the burden of proof differently, and they have different sensitivities. But in every case, you need high sensitivity tests in order to have an unambiguous sort of conclusion of a statistical hypothesis testing exercise. So the second major point that I'd like to leave you with is that it's not just the definition of replication that's not as simple as it seems. The analysis of replication is not as simple as it seems. Approximate replication is certainly more attractive as a scientific, more useful as a scientific approach, but the analyses are even less powerful than for exact replication. And placing the burden of proof on replication may in fact be attractive from a logical point of view, but it's even less powerful. I won't go into the details now, but trust me, that's true. So where does that leave us? Well, that leaves us with the other obvious thing about replication, which is how to design replication studies. And remember, people pretty much, I think have the idea that designing a replication study is pretty simple. You just repeat the study, maybe you make it a little better, a little bigger, something like that. But this is not rocket science, designing replication studies. It's just repeating and maybe improving on what was done in the first study. So let's look at that a little harder. Basically, what I would like to do is say that in order to really think carefully about studying replicability of findings, you need to take a step back and say the problem is designing an ensemble of studies, at least two, that when taken together in the analysis will yield unambiguous conclusions. This is a problem of research design, of experimental design or multi-experimental design. And people haven't thought much about it, but they really need to, and I'm going to show you why. I'll also say you've got to include the original and the replication study in thinking about this as a system, because in a certain sense, there's nothing special about the first study. The first study just happens to be the first study. Once you have two studies, the question is, do they get the same answer? And you can't say that the first study, for example, it doesn't have any uncertainty in it, because you have to think about the ensemble of the two in order to evaluate the total uncertainty the two estimates produced. Okay. Well, again, without going into details, the power of the Q-test, in order to, the pitch I've made earlier is that in order to really do a statistical analysis of replication that's going to be unambiguous, you need to know something about the power of the test. If you're going to design an ensemble of studies, you need to know something about the power of these tests in the ensemble you're going to use. And it turns out that the power of the Q-test depends on a quantity which I've labeled lambda here somewhat confusingly, I guess. But you'll see it's actually the same thing. It's the weighted sum of squares, or the standardized squared difference of the two effect parameters. And how big that is determines the power of the Q-test. And so how would you compute the power of a test? Well, you try to figure out what the smallest difference that was non-negligible, or the largest difference, perhaps. You'd have to figure out what you need to. It's like the exercise of picking an effect size when you do the power of a randomized trial or something. You either pick an effect that you think is likely to be there, or you pick an effect that you want to be able to detect if it is there, a degree of heterogeneity or non-replication that's big enough to have serious implications. And once you've specified that, then there's a rigmarole for working out the power of the test. So now I want to sort of do a little exercise with you that I think will lead to a surprising result. So suppose we've got two studies, and we want to go through the exercise of saying, well, how big a difference do we really need to detect? I mean, that's going to be a judgment call, and different people will come down differently on that. But you can think of the judgment I'm asking you to make as saying this, that suppose there is a true effect in study one, then how much different does the effect in study two have to be for you to say that's a really important difference. Now, I'm going to argue that sign matters, to your point, that theta 2, if theta 2 isn't also positive, then I don't know how you can say the difference between theta 1 and theta 2 doesn't matter if you get a qualitatively different result. So what I'm really saying in this slide is, okay, according to me, and I think it's not so implausible for all of you, the biggest difference that could be negligible from theta 1 is a difference that leads theta 2 to also be positive. Now, I'm requiring, symmetry in that a difference in the positive direction, a difference in the negative direction matters just as much. But if you buy that little caveat, interesting things start to happen. One of the interesting things starts to happen is that you see that you can define the non-centrality parameter that you ought to be caring about for powering the test. And the biggest difference between theta 1 and theta 2 that you can get and still have theta 2 be positive is essentially when theta 2 is just infinitesimally bigger than 0. So the biggest squared difference between theta 1 and theta 2 that you could possibly say you don't care about is one that leads to lambda being theta 1 squared over the sum of the two variances. That makes sense to people because after all, so what we're trying to find out is, what non-centrality parameter should we use as essentially the smallest, the biggest effect anybody could possibly say is negligible, or the smallest effect anybody could possibly say you need to care about. Now, the reason this funny little exercise with algebra is important is because, well, it gets a little tricky here. We just discovered that the largest negligible non-centrality parameter is theta 1 squared over the sum of the variances, and any other negligible effect has got to be smaller. So we've got a power for detecting an effect that's equal to theta 1 squared over v1 plus v2. And now where it gets interesting is that if I now ask you to shift gears, and let's talk about the hypothesis test for study 1. Study 1 tests the hypothesis that its effect is 0, and it turns out that the hypothesis test for testing that the effect is 0 in study 1 is also determined by a certain non-centrality parameter, and that is theta 1 squared over v1. Now, the reason this is interesting is because in both cases, the power of the test is determined by the same rigmarole. They're both, can be thought of as chi-squared random variables, and so what this means is the very same relationship between the lambda that determines the power of the test of the null hypothesis of no treatment effect in study 1, this lambda has the same relationship to power as that lambda has for the power of the replication test. And so the theorem is the power of the test for replication has to be less than the power of the test in the first study, because the only way you can get, and now I'm wandering around, which I shouldn't be doing, and the only way you can get this to be equal to that is if v2 is 0. If v2 is bigger than 0, which it almost always will be, there's going to be some uncertainty to any experimental result, then this, which determines the power of the replication test, is going to be smaller than that, which determines the power of the test in study 1. Does that seem to make sense to people? Did I go the right direction? Yeah. But it's worse than it seems. Because the power of the test for non-replication is actually likely to be much less than the power of the first study. suppose the two studies are exactly the same. Suppose you do what the average scientist would say is the right thing to do. How do I do a replication test? Well, I repeat the study, do it the same way, and I see if they get the same answer. Well, the test for whether they get the same answer, if the two studies have the same uncertainty in their effect size estimate, actually that means that the non-centrality parameter controlling the power of the replication test is now only half as big. And just to show you how that ramifies through to power, if you repeat the same study, and the first study had 80% power, the replication test will have 51% power. It's only if the second study has an infinite sample size, which of course you can't do, that gets the replication test up to the same power as the original study. And just as a trivia fact, if you ask the question, well, how much power would the first study have to have in order to get 80% power for the replication test, the answer is 98%. And any of you who've ever done a power calculation for a large field trial know that nobody is giving you the money to power these things at 98%. Well, if you find a funder who's doing that, tell me who they are, because that will be real interesting. So this finding, I don't think people were aware of before, but once you see it, it really gives you pause. And just for fun, I've given you the pitch that approximate replication is really much more scientifically useful as a way to think about replication. Well, that test has even less power. We said that before. Remember, the approximate replication test is less powerful than the exact replication test. Well, this is all computed on the basis of an exact replication test. And this is also, this theoretical finding also assumes that if you replicate a study and both effects are positive, you declare victory and go home. But a lot of people wouldn't say that that's what they mean by, my intervention study replicated his intervention study. My effect's only a half as large, but it's the same, right? Well, maybe we shouldn't, some people wouldn't accept that. And of course, all of this changes, and it gets even worse if you start saying, well, it's an effect that's half as big doesn't really count as negligibly different.
Can I ask a really stupid question?
Oh, it's not going to be stupid, Lori, if you're asking it, I'm sure.
No, this is like going way, way back, but because I'm following the power limit, but I don't know what theta is. Because when you first introduced theta, it sounded just like population sampling.
Yeah.
Then, when we talk about effect sizes, it sounds like variation in intervention or treatment effect.
Could be.
But
Yeah, well, it is,
if
actually.
the studies differing, they can differ by population sampling, by the intensity, let's say, of the treatment,
Yeah.
by context, and by the methodology of the study.
Yeah.
So now do I understand that theta is the variation in all of those things?
Theta varies because of all of those things varying. But here's the here's the problem. And what you're pointing out is that there are a lot of cases that really aren't, in which the same treatment is investigated, but they really aren't replications. And the danger, so part of what I'm pitching, by the way, is, it sounds like I'm saying we ought to do what CODATA does and do these big meta-analyses of things and establish constant values. That's the reason I went there, was just as an illustration of even when you have things being constant, it's really complicated. But what I am trying to do is raise the level of thinking and discourse, and for us also defensive discourse, I think, about these issues of replication, because there are going to be people who will want to say, here are 5 studies that they actually differ in the way in which the treatment was implemented, they differ in the population that was studied, they differ in the context in which things were going on, and lo and behold, they don't agree. This is a terrible threat to the validity of education or behavioral science or whatever. So I think the point you're making is precisely the kind of thinking I would like people to be doing, and in responding to what I think the challenge is going to be to us, because people are going to do something very simplistic, and then they're going to beat us up with an equally simplistic notion of what replication is, but also they're going to miss the point that the thetas probably are not supposed to be the same. Now, there are examples. I will say, though, that remember that if the Center for Open Science, for example, thinks there are examples in which psychology should be as replicable as physics or chemistry, and maybe they're right for some things. There probably are some things in which that's true. By the way, you can. There's another way. There's another spin you can put on all this stuff, which is to say we have a collection of studies. There's a set of covariates that determine which studies should be getting the same answer, and the analysis we should be doing should be conditional on that taking into account the differences among studies. And it turns out also that the generalization of all this Q-test stuff just is very simple, to a conditional model, a meta-regression model. So there are ways to take your caution into account, and we should be thinking about it this way. But we also have to be really careful, because if what we say is essentially no study we do can ever be replicated, so fortunately this replication problem, this replication criterion doesn't apply to us because we don't do things that are ever the same twice, that's a dangerous position to be in too. So as a science, we have to figure out what we think about this stuff. But even in the realm of actually trying to do exactly the same thing over and over again, I don't think you should expect to get the same answer. And by the way, part of the implication of what I'm saying here is that if a funding agency, for example, is going to decide they want to fund replications, and then they're going to evaluate the replications, they should not fund 2 studies and expect that they're going to learn anything that's unambiguous. And I think that's a message people are not going to want to hear. By the way, the Center for Open Science stuff also, it's a terrible design that they chose to have a whole bunch of different things replicated once. So there's a lot to be learned here about how to think about this issue, I think. Yeah?
Isn't this just like a likely explanation for the reproducibility crisis then? Like, none of these reproducibility studies have the adequate power to detect that original effect size.
Well, it's kind of worse than that, because many of them don't. One of my social psychologist friends said, oh my gosh, people are doing studies with 4 people in them. I guess the implication of what you're saying is that none of those are going to be very likely to be reproducible, and the answer to that is sure. The Center for Open Science found a bunch of cases in which things didn't reproduce. But that's scary, because the power of their tests was low enough that they got lucky when they found those things. And so my real point in all of this is to try and bring the standards of methodology and evaluation of this stuff up to the level of what we do in other areas. If you send a proposal in to do a big randomized trial, and you don't explain what analysis you're going to do, and you don't explain why the funding agency should believe the study is going to be unambiguous, you're going to be triaged out of the discussion. And yet some of the work that seems to be being done now doesn't take into account that there's a methodology that needs to be applied to thinking about whether results are likely to be ambiguous or not, and what you have to assume in order to make that claim. And my pitch is for us all to be doing that kind of work, and also to be having a more sophisticated view of what we think about replication, because I think that scientists are surprisingly naive about this, and I include myself, because it's only slowly dawned on me. Each of these points that I'm making have only slowly dawned on me over time as I've paid attention to it, and I realized, geez, I didn't think about this in a very clever way, and I work in meta-analysis, so I should have known better. Let me say a couple other things before we go. Major point 3 is that it's impossible to obtain it may be impossible to obtain a test for replication from a single replication study that's sensitive enough to be conclusive. And that's something we should not waste our money on trying to do something that's impossible. You can increase sensitivity with more studies, but there is a question at some point about whether or not the resources ought to be expended for that purpose. But a really big point is that we need better work on the design of ensembles of studies for testing replications, because if any funding agency is going to be putting money into this, they ought to be putting money into things that have some chance of yielding conclusive results. I'll say a supplemental point, and this is also obvious once you think about it, but not obvious until you do think about it, and that is that some people have said, and the Center for Open Science is also, the mini lab studies actually have this character, and it's another mistake, not to beat up on them too much. The fact that they're actually trying to do this stuff is great, and it's only when people start to do stuff in a new area that you begin to realize, how you can screw it up. But the emphasis has been, there's a mini lab study in which 35 labs have been recruited to all do the same experiment. So now they have a set of experiments, and 35 labs are basically doing the same experiment. So the first case they had 1 replication, now they have 35 replications. But one of the things that they're stressing is the comparison of all the replications with the original study. And that sounds smart enough until you think about it in the following way. If you combine the results of the 35 replications, you've got one synthetic study, which you're comparing to another study. And what we just proved was that when you compare 2 studies, the power of the test for the difference is determined by the weakest of those studies. I didn't actually say that, but it actually turns out to be true. There's nothing special about study 1. So if you take 35 studies, combine them all into one synthetic study, and compare that result with the original, you're back to this 2 studies problem. And exactly what's true about 2 studies is true about that situation, even though you've got many more studies. The key is, and it's not obvious until you start thinking about it, that the way in which you can get more sensitive tests for replication if you have several studies is by comparing each study with every other study. And that's what the Q statistic kind of does. Compares each study with every other study, and by doing that you wind up being able to get more sensitive tests. But this point illustrates how this stuff is tricky. Smart people have made, have sort of gotten tripped up by little things, and that's why you need methodological research. And that's just the point I was going to make in my last slide. And now I'm prepared to thank you and shut up. Or to be disputed, depending on.
I think we have time for a few questions, but before I do that, I neglected to introduce Kathy Schultz from the School of Education and thank the School of Education for being a sponsor. So thank you, Kathy. All right, questions?
And now feel free to argue if you want to dispute my premises or the logic connecting premises and conclusions.
Jason?
So, I've served on probably half a dozen editorial boards of fairly influential journals in different disciplines in the social sciences.
Mm-hmm.
And each time I say, I would love it if we could have 20 pages at the end of each journal,
Mm-hmm.
or called, we call it replicate this,
Yeah.
whatever we wanted to say it, and
Yeah.
you publish findings either within that journal that I just found.
Yeah.
And it's a very clear, it's a 1-pager or a 2-pager.
Yeah.
Replicate that key parameter estimate.
It's great idea.
I can't get any enthusiasm for that every single time, and I'm wondering if you have any insights about what it is about science writ large, social sciences specifically, that may have you nodding your head as I was talking, like, of course they're not going to want to go that way. I'm just looking for your answer. to try a guy next year.
Yeah, every discussion I've had about this, the woeful lack of replications, sort of has somewhat the same tenor that gosh, how can we get people to do more of this? And the NSF had a meeting about this. The Social and Behavioral and Economic Sciences group had a meeting about this, and almost all of the discussion sort of eventually turned to how can we change the culture of science? And that is, culture change is a hard thing. The one thing that impresses me is that the Center for Open Science has managed to get all these people to do these replication studies. And I don't know, I never would have believed, if you had asked me to bet on that, I would have bet they would never get these studies done. So, but of course, they're doing very much laboratory stuff, and it's laboratory social psychology for the most part. And I mean, it's easier to do experiments if you can do them in a lab. The short answer is we have to collectively value this more. We have to we as scientists have to collectively value replication more than we do. I mean, we say we do, but really we don't. And we say things like, sure, replications are important, but you don't want to publish a replication in this journal. We only publish new stuff. And the argument is that generally that new findings are more important than the replication of something we already know, which is kind of crazy because the logic of science says we kind of don't know it until we know it can be replicated. So we've got ourselves into this crazy situation where journals get impact factors by publishing sexy stuff. What is sexy? Sexy is new. New England Journal of Medicine is sort of, in some ways, is a sort of interesting example. They publish a lot of stuff. They seek out things that are, in their view, sexy. And I think replicate. I don't think you get. I just can't. I think it would be real hard to get a replication published in the New England Journal. Not that it doesn't sometimes happen. I don't know a good answer except we have to change the culture. That means how we educate our students. So that they understand that replication is an important part of science, not just something we give lip service to. We have to begin to understand that if we don't take this on, it becomes the province of people who make their careers by showing how research findings can be upended. There's this whole business about p-hacking. Which is how you get your p-value, just below 0.05. Well, why does that happen? That happens because there's a whole set of incentives to get significant findings. Well, now we're in an era in which there's an incentive to get non-replication because that's a sexy thing to get, maybe, at least among some groups. So this creates an interesting situation in which people have an incentive not to replicate things. Of course, their rhetoric wouldn't be that, and maybe they wouldn't even think of themselves that way. But the fact is, a young researcher can get a lot of prominence by overthrowing some result that was thought to be known for a long time. And so we've kind of created a monster for ourselves, and we have to and we're going to have to deal with that in some way. And I think we have to, hard as it is, try to change the culture. And with respect to p-hacking and other things like that, but also with respect to replication. And the idea of short replication papers, that's a great idea. And if they could be valued as much, if they could be valued, not necessarily as much as an original study, but they ought to be easier to do than a brand new study, then that could create a pathway for a young researcher to do replications and not sacrifice their career. Now, how we do that is a real. I don't think I know the answer to how we make that little culture change, but it does seem to be an opening for us, and it's going to be senior people of goodwill. You will be able to have a role, and I will be able to have a role maybe, and then it's going to be young people who are taken with a different view of science than. You can always find some way to get a significant result out of this and get it into a journal. that's not inspirational, you know, and I hope young kids will, young researchers, you know, I'm old enough to call young researchers kids, I hope young researchers will be inspired by a different vision of science than I can sneak it into a good journal no matter how bad it is, because that's the right careerist thing to do. But we don't want them to actually destroy their careers in doing that, so we have to help, we have to enable, if you will. I think you had your hand up first, then we'll come back to you.
Well, just one comment on that, the changing the culture piece, and then I had a question too.
Yeah.
So I actually work with the Laura and John Arnold Foundation, so one of the things that we're trying to think about on our team especially is how funders can play a role in changing that culture too.
Yeah.
Because it's the same sort of value that the journals have. Funders, it's like, oh wait, you want to study something that's been studied before?
Yeah.
We did. That's boring. That's not a splashy headline.
And let me just say, your foundation deserves a lot of credit for many good things, including supporting the Center for Open Science. So it may sound like I've been very critical of what they've been doing, but I'm not. You know, it's kind of like the talking dog. It's remarkable it can talk at all,
Right.
and so I am.
It's all fair points, and it's also a different team in the foundation that funds it, so not at all.
Yeah.
But so one of the things that we do on our team is we fund RCTs, and
Mhm.
one of the key criteria we're looking for are you're coming in with a strategy that already has some prior evidence of effectiveness, whether from a trial or so we're trying to actually incentivize people to do replication trials, and basically saying that you will be more likely to get funding
Mhm.
if you are evaluating something that's already been evaluated at least in some form before.
Yeah.
And starting to think about how we can talk to other funders about getting them thinking that way too.
I really hope that you will, because the broader issue of getting funders to actually evaluate what they do, I think many foundations are happy to declare victory when they fund something, and the question of whether or not their programs actually have had any long-term impacts is not important enough to pay attention to. So your foundation deserves a lot of credit for trying to raise these issues, and I wish you very good luck in doing it.
We'll see if we can get any traction. The question I had is on the sort of getting more into the details of the replication statistics. How do you factor in with the original study sort of the file drawer problem? That original study may not be the first finding.
Yeah,
It's actually
yeah.
one of 4 findings, and it's the most promising.
Or 40 findings.
Or 40, and it's the most promising of those. So
Well,
how do you think about discounting, I guess? I guess it gets into the negligibility.
yeah, this is actually an interesting point, because as somebody who worked on methodology for meta-analysis, one of the things I did back in 1984 was write a paper on what the impact of publication bias could be on estimates, you know, and there's a principled way to actually deduce that, and it can be pretty huge, and there are a variety of sort of models for adjusting for publication selection, and the high-end version of them, the low-end version of them, well, there are a variety of methods, I'll just say that, and they vary in their plausibility. But one approach, and really everything I was saying now applies in a strict sense to a set of registered replications, you know, so not where you don't have to worry about publication selection. But when you do have to worry about publication selection, then I think the right thing to do is to at least consider taking it into account. And when I say, you know, the reason I don't say absolutely every time, no matter what, is that the good approaches, from speaking as a statistician, the statistically sound approaches, I believe, to adjusting for publication selection involve either assuming a selection model, which is basically, you know, assuming something you don't know for sure, or estimating a selection model from the data, which adds on, and either of these things adds uncertainty to the original estimate. So what you might think is that it's a slam dunk that you ought to adjust the first estimate for publication selection. But the question is, does the adjustment for publication selection add more uncertainty than the effect of the bias it reduces? And it's a tricky question. In a lot of cases, it's better to adjust, but there are cases in which it's not better to adjust, because what you then do is play into the idea, I've made the uncertainty of the first study's estimate so big that, you know, everything's going to agree with it. So that's the tricky issue. And one of the things that I think is probably the right thing to do is an operational sort of analysis. And the first thing to do is design the ensemble of replications. If you're doing this intentionally, you ought to design that replication of the ensemble of replications so that in principle you have enough power to do things. But then you ought to at least evaluate the question of, well, suppose I adjusted the first study for replication, for sample selection, publication bias. How would the analysis come out? And suppose I didn't adjust it, how would the analysis come out? And that brackets probably the two conditions you want to know about. And if you're lucky, you get the same answer. If you're not lucky, you get a different answer. But sometimes that may be the best that we can do. And so you definitely, the answer is you shouldn't ignore the possibility of publication selection. But on the other hand, it's too simple to say you should always adjust for it. And there's another thing that I'll just mention because I think it's of the same kind and it's a down in the weeds thing. So now that we're in the weeds, we might as well talk about another thing's down in the weeds. I found it fascinating that the particle data group throws out such a large number of their studies. And then they have this criterion for what they declare negligible heterogeneity. Now, we have done some work on what's the impact of heterogeneity tests if you throw out the most deviant things, and it makes a really big difference to throw out the one or two most deviant studies. And so I actually think that from a strict statistical point of view, what the particle data group is doing is they are fooling themselves about how homogeneous the studies that they're looking at are after they toss out really deviant values. I also have enough respect to say they've been doing this for a long time. They seem to be gaining greater understanding of the physical world. Who am I to tell them, that their statistics is perverting their science? Just saying it would be tough to get this published in a statistics journal. But and we ought to be aware of that too, because there's kind of the tendency to say, I looked at a bunch of studies. Oh well, there was this one, and it's wrong for some reasons. Mostly because it disagrees with the others. And wow, everything else agrees. Pretty much. We got to be careful about fooling ourselves there too, because it makes a really, really huge difference to throw out one or two of the most deviant possibilities just because they're deviant. Anyway, there was another question. So,
last question.
Okay. So this half question, half observation, which is that I think that it's probably worth making a distinction between replication, and I'll use replication and reproducibility.
Yeah, absolutely.
Right?
Yeah, they're different things.
First I was going to say I think we should make a distinction between replication and reproducibility,
Mm-hmm.
but let's just collapse those for the moment, because I do think we probably want to make a distinction between replication, reproducibility, and generalizability.
Oh yeah, absolutely, absolutely.
Right? And I think much of the spirit in the work you've done in meta-analysis is really asking the question about generalizability, which is to say, when I vary the instance of the treatment, when
Mm-hmm.
I vary the sample that I use, when I vary the kinds of covariates I have,
Yeah.
how do I see that the effect is changing, right?
Yeah.
And I think one of the things that in education in particular we're not very clear about is sort of at what range are we willing to accept as exchangeable
Mm-hmm.
different samples,
Yeah,
different
yeah.
Outcome variables, different covariates, such that we would consider it to be a replication if you did the same thing, as opposed to asking the question of whether the effect generalizes.
Yeah.
I think there's a gray area.
There absolutely is. There's a bunch of interesting work. I've done a little of it, and other people like Beth Tipton at Columbia and Liz Stewart at Hopkins have done others of it, trying to sort of formalize ideas about the fact that most randomized trials have non-probability samples, and yet people want to take those studies and make claims about applications to populations that don't look anything like the study samples. And so I think it's really, I think that this isn't exactly where you went to begin with, but I want to mention it because I think it's really important work, that there is this sort of better work about how to make generalizations to inference populations. Essentially, the way the sort of the gist of all of it, the techniques are slightly different, but it boils down to asking the question: what would the treatment effect that we observed in this experiment look like if the composition of the inference population, which may include characteristics of context and things like that, so take the experimental sample and ask the question: if the experimental sample had the same composition as some inference population of interest, how would the treatment effect have changed? And the reason that's an interesting question to ask is not because it subsumes everything you might want to know about generalization, but it has the important property that it forces you to think seriously about the inference population that you care about. And having been on projects where we're actually trying to do this, it's really interesting how you go from, oh, I mean all the schools in the state. Oh, wait a minute, no, I don't mean all the schools in the state. I mean all the schools in the state that are co-ed, and and actually I don't mean the deaf school, and I don't mean the this, and I don't mean the school that's in the prison, so that's one thing that disciplines us. The other thing is that it disciplines us because when you start doing this work seriously, you actually have to know a lot about the composition of the study sample and a lot about the composition of the inference population you care about. And a lot of times people don't know much about either of those things. And then the third thing that is particularly important to me anyway is that when you start doing the technical work, you see that to the extent that the inference population is dissimilar to the study sample, the inferences get bigger and bigger standard errors. And so you get to the point where sometimes an experiment can tell you a lot about one inference population, but virtually nothing about another one. And when I say virtually nothing, I have this example in my mind because we did it. A Tennessee class size experiment is really good for inferring to the state of Tennessee, and it's pretty useless for inferring to the population of Los Angeles, meaning that the treatment effect was 10 and the standard error was 50 or something. And so, okay, well that means you don't know anything from this. And forcing us ourselves to actually confront the limitations of what we do know, I think is really useful in the generalization area. But I take your point that meta-analysis, one of its principal uses in the social sciences has been to support generalizability claims. What people kind of, and what's interesting to me is what people kind of missed when you start talking about replication, like I've been talking about all these meta-analytic statistics, is that meta-analysis isn't fundamentally about combining evidence to support generalizability. It's about combining evidence, period. and some of those applications are like the ones that I was talking about today. I mean, when the particle data group does meta-analysis, they're not thinking about generalizing. They're just trying to get a good answer to the question, what's the mass of the electron? And so I think even I agree with your claim about the use of meta-analysis, but it actually it doesn't have to just be used for that.
Okay. Thank you very much.
My pleasure.
Thank you all for coming.